All right. In this video, we are going to take a look at variation, both inverse and direct variation. And mostly this is going to be about doing example problems, but we do want to point out a few things. First of all, the words that you want to be listening for in the description, the word directly, which we have up here, always means what the variable that comes after that is going to show up in the numerator of the equation that you write. And if you instead hear the word inversely, then that means the variable that comes after that is going to be in the denominator. When we write our variation equations, we always need to include what's called a constant of variation, and we'll talk about that in these problems about why that has to be there, and we usually use the letter K for that, although in some specific problems that value, that constant of variation, actually has a very specific name. So let's take a look at our first example here. It says, starts right here, that the volume V of a gas varies inversely. Okay, so there's our inversely word that we were looking at, as the pressure, which we're using a variable P to stand for the pressure, and directly, so this actually has both of the words, as the temperature T. And it wants us to write an equation that expresses this relationship. Well, it's going to be the volume V. Okay. It varies, so we've got our equal sign there. Probably right off the bat, worth putting in our constant of variation. And it says it varies inversely as the pressure, P, so the inverse one is going to go into the denominator and directly as the temperature T. So that is our equation that represents the statement of the volume of the gas varying inversely as the pressure P and directly as the temperature T. Sometimes they'll have you stop there, sometimes they want you to go a little bit farther. So in order to go a little bit farther, what we need is some information that will allow us to calculate what the value of K is. So this says that a particular gas at 2 atmospheres of pressure, so there is our P is going to be 2, and 280 degrees Kelvin, that's our temperature, is 280, is sealed in a 10-liter container, so our volume is 10. And if we put those numbers into our equation, then we get 10 is equal to K times 280 divided by 2. There's only one variable left, so we should be able to solve for that. I can do 280 divided by 2 and get 10 is equal to K times 140. And then if we just divide both sides by 140, my zeros can cancel out there and tell me that K is equal to 1/14. So the next step that I take now is to go back to this problem that I had up here, and I'm going to rewrite that with the value of K in there. So V is equal to 1/14 times T over P. The 1/14th would have something to do with the particular gas. It's a characteristic of this particular gas, and different gases would have different values of K, but the relationship between them remains the same. So now it's asking us, what would the pressure be if the same volume, that same 10 liters, was heated to 300 degrees Kelvin? Okay, so we're going to make some substitutions. We're the same volume, so we still have the 10 is equal to 1/14 times the new temperature, which is 300 degrees, divided by the new pressure, which is what we don't know. That's what we're trying to find. Okay, so I'm going to move this up a little bit where I got some room to work with it and minimize these calculations. Get those out of the way. In fact, I think move that up there too. So we can do a little bit of simplifying here. We could write this as 10 is equal to 300 over 14p. And then if we cross multiply those like we did back in our geometry days, we get 140p is equal to 300. So we just need to divide both sides by 140. P will be 300 over 140, or 30/14, or 15/7, or 2 1/7, which is approximately 2.14 atmospheres of pressure in that problem. All right, here is our second problem. We'll take a look at this one. It says that the period T of a pendulum varies directly as the square root of the length L of the pendulum. Okay, so fewer variables in this one, but we can start. It says the period T varies directly, so I'll get my constant of proportionality in there. And what does it vary directly as? It varies directly as the square root of the length. So that K is going to get multiplied by a square root of L. Okay, so that's our general equation. We're going to drop down then to a 1 meter long pendulum, swings with a period of 2 seconds. So that says if the L is 1, then the period T is equal to 2. And so that's the information we need to be able to calculate the K value. We write T, sorry, we actually know the T. Our T value is 2, is equal to K times the square root of 1. Well, square root of 1 is just 1, so it says the K value in this case is 2. So now we have an equation that looks like T is equal to 2 times the square root of L. And it asks how long is a pendulum that has a period of 4 seconds. Well, the period's twice as long, but we're going to find out that the length is not twice as long. So our period of 4 seconds, we'll put that in for the period variable, is equal to 2 times the square root of L. And so the square root of L is equal to 2. 4 divided by 2 is 2. And if we squared both sides, we would find that the length of this pendulum then is 2 squared, which is 4. And our measurements were in meters there. So we've got a 4 meter long pendulum. The pendulum has to be 4 times as long in order for it to have double the period. And we'll leave it for an exercise for you on the notes to figure out what might change that value of K as you do a little more research on pendulums.